Okay, so today's class is basically, I think we are going to be working on the homework, so that should be page. Oh, this marker is much better. This is thermodynamics. Today is 3/8, and this should be lecture 15. Yes. Okay. Okay. So basically, today is homework. So basically, is the day you can ask me any question you want about the homework. So do you have questions about the homework? Okay, go ahead. Okay, let me look at it first to see. It's chapter 4, is that correct? Yeah. So 473. So let me go to 5, might be easier. 73. Oh, 73 is this one. Let's just do it. You want to do that one, 73? So let's see how can I do this. Is it a way for me to where's the page? I need to find out where's the page. So here. Okay, zoom 1.5 might be too much. 25. Can you read, or is it too small over here? It is what it is, huh? Is it okay? I don't need both columns, but what happens is that if I make it bigger, I need the height. So it's, I don't mind. I mean, let's try to do 85. And I can scroll down. But I don't mind to do, is that better? Okay, and we work it out, okay? So 473, let's go ahead. Okay, that looks like a classic problem. So problem 473. So as shown in figure 473, so what I'm going to do is I'm going to copy the figure and then I'll go back to the problem statement and see if there's anything missing. So it looks like there is some type of big heat exchanger here. Okay, and again, you see that even though the problem statement is there with the figure, I still go and do a figure, no? Inlet here. Outlet in there. So it looks like there is refrigerant R134A going into the pipe here at point 1, and we know that P1 is equal to 70 lbf in squared, T1 equal to 160 degrees Fahrenheit, and the mass flow rate of the refrigerant, so M sub R, is 3,100 pounds per hour. Can I do what? Sorry? Yeah, no, this is just the line to say 1. So, is that correct? Yeah, that was just to say point 1, like the line they have I mean, I cannot do it, but like the line they have, or no. I was just doing like this line over here, but I did on top. Okay? So just say position 1. And now, so this will be now here. So this again, position 2. So yeah, the arrow is going down. And we know we'll be exiting at a pressure of 60 lbf in square. And what would be the state? We know this would be saturated liquid. Okay, so then what do we have? So on the other side, we're gonna have a pipe with cooling water. So let's say this is A, this is B. So it's water going in. Water coming out. And it looks like here they just give you the difference in temperature. TB minus TA equals to 20 degrees Fahrenheit. P sub A equal to P sub B. Okay, and this is also equal, it's just to look at the difference in temperature, so it's 20 degree Rankine, it's also 20 degree Fahrenheit. All right, so let's read the problem statement and see if we're missing any information. I hope so, because I don't see much information on the problem statement. So, as shown in figure 473, refrigerant 134A enters a condenser operating at steady state. Okay, so is the term steady state important? Yeah, because it means then that, so let's see, steady state. If we have to do an energy balance, will mean that the energy generated is 0. Okay? At 70 pounds force inch square, 160, so that's already in the, and is condensed to saturated liquid at 60 pounds psi on the outside of the tubes through which cooling water flows. In passing through the tubes, the cooling water increases the temperature by 20 degrees. Okay. All right, and experience no significant pressure drop. Cooling water can be modeled as incompressible with V, okay, with V equal to, okay, so let's say water so for water, they say we can take the specific volume to be equal to 0.0161 cubic feet per lb, and C, which is the specific heat, be equal to 1 BTU lb degree Rankine. The mass flow rate of the refrigerant is 3100. That's already on the figure. Neglecting kinetic and potential energy. So if you want, I can just put here on the figure. Kinetic and potential energy equal to 0. And ignoring heat transfer from the outside of the condenser, determine. Okay, so we need to find, let's say, A and B, the volumetric flow rate of the entering cooling water in gallon per minute. So what is the volumetric flow rate? Is velocity times A of the water in gallons per meter, and the rate of heat transfer in BTU to the cooling water from the condensing refrigerant. So basically we need to find Q, okay? In BTU hour. Okay, so I have to be honest with you, right now I don't really know how to solve this problem, but we'll probably find the solution, okay? It's like I always say, you know, many times solving problems is like going into a tunnel. You are used to getting into a tunnel and you like to see the exit, no? Okay? This is like getting out of a tunnel and you don't see the exit. So you need to start getting the tunnel, it's dark, and need to start working, no? And by moving forward, we might end up seeing the light. So over here, the first thing I'm going to do, I'm going to try to write down an equation. So I'm going to select this over here as our system. And see what happens. Okay, so the first thing I'm going to do is I'm going to try to write down as many equations as I can and see if I can relate them in order to solve the problem. So here we go. So first thing I'm doing is applying to go a little bit faster. Applying energy balance, but which is the same thing as first principle. To the system, what do we have? I mean, okay. So, by looking at the figure, oh, I should maybe move this. See? Okay, when I look at the figure over here, do we have, okay, so let's see, do we have any heat going in or coming out? Yes? No? No, so this is 0. Do we have any work or anything done on that system? Okay, everything comes from the figure, no work. So now, what is coming in? We have coming in what? We have refrigerant 134, no? At 1. So that would be MR times, and the energy can come on the what form? Kinetic, potential, internal, and work done by the pressure, no? So there is no kinetic, there is no potential. So the energy coming in will be coming under the form of what? Enthalpy that combines the internal energy plus the work done by the pressure. Okay, what else is coming in? M of the water, H sub A. Okay? Now, so that's equal to what? To whatever is coming out. So what is coming out? Refrigerant, M sub R, times what? H2. And what else is coming out? M of water at H sub B. Okay? So basically, over here I could rewrite this as what? M sub water will be equal to what? H sub A minus H sub B Maybe I should have done it the other way, but it doesn't matter. Equals to what? M sub r h sub 2 minus h sub 1. Okay? So from here, let's say I could write M of water would be equal to what? M of the refrigerant, H2 minus H1, divided by HA minus HP. Did I do a mistake here? No, that looks fine. Okay, so this is our first equation. All right, so now what I'm thinking in my head as I'm solving this problem, do we know MR?
No.
What do you mean no? MR is given to us or no?
Yeah.
So, you know, this is, I mean, you don't need to write it down, but in my head, this is what I'm doing when solving this problem. MR, we know, okay? Can we know H1? Probably we can find it from the tables, no? Yeah? So that should not be a problem. Do we know H2? We can probably find it from the tables. All right? So the problem over here for me would be HA and HP. Okay? All right, so I think here comes the trick of this problem. I'm guessing, okay? So, that would be a question. Oh, for the water. No, so for the water. So the water, I mean, they don't give us really this the answer, but what I'm thinking here to solve this problem is that the water is at entrance A and entrance B. They say it's incompressible. So that means, so I'm saying it remains in the same state, which would be liquid. Okay? So if it's on the same state, the change in enthalpy is proportional to what? Remember, that was one of the important things I told you, is that the change in internal energy is proportional to what? C sub V delta T, and this should be proportional to C sub P delta T, no? Yeah? So over here, I could approximate this by what? I could say then that H sub A minus H sub B is basically proportional to what? C times what? T sub A minus T sub B. I don't know why they give us T sub B minus T sub A. Because no matter what, one will be, okay, so that will be the second equation we can have. Okay, and all this is equal to what? This is equal to a delta T, which is equal to what? To 20, no? Yeah? So basically now we know MR, we know H2, we know H1, we know the one at the bottom. So we could say over here, so that equation 1 becomes what? So we have M water will be equal to m sub r of H2 minus H1 divided by C delta T okay, maybe here I'm going to combine another equation. Now, by definition, what is the definition of the mass flow? Is volumetric flow rate AV divided by what? Specific volume V, no? Yeah? So from this equation you get that the volumetric flow rate AV is equal to what? Mass flow of water times the specific volume, no? Yep. So finally, what do I have? AV, volumetric flow rate of water, will be equal to what? So M refrigerant times H2 minus H1 divided by C delta T times V. So you see that I've been able to solve the problem, everything conceptually, no? Okay, following the process. So now, in order for you to finish the problem, what do you need to do? You need to go to the tables and find what? H1 and H2, no? Everything else is known, correct? So I guess you can go and finish this problem on your own. So this is from tables. Okay, so you see in an exam, if I see this, even if this problem is 10 points, you probably get minimum 8, and if everything is clear, you probably get 9 points. And you haven't put a single value, no? But you are showing me that you understand how to solve the problem. Okay? So this is what I'm looking for. You to show me that you understand the material. So do you have any question about this problem? See, I didn't put it. They are not really values. So over here, what is the important part? That was the tricky part, because we haven't really covered it yet much. Is this equation over here, no? Yeah? Yes?
So we originally had Q dot equaling 0, but then it's asking...
Oh, sorry. This I just did the part A. Sorry. Thank you. So all this stuff is part A. You're right, I was. So this is find the volumetric flow rate of the water. Okay? And you work out the units. So now, part B, sorry for that. See, thank you. So part B. Oops. It broke, it doesn't matter. Okay, so part B, we need to find Q. So over here, let me just do one little piece of the figure we had of the tubes. Okay, so this will be here. Let's say it will be, maybe I did it bad over here. It doesn't matter. Let me change because we have the possibility. Let me just change the page. I don't want to confuse anyone with the figures, so 89. So part B. So what I'm doing over here is that I'm taking this Fibonacci diagram and I'm just going to do one little piece over here. So okay, so imagine this is the green tube. And let me just do it this way, okay? Well, this will be A, and this will be B. So if you want to make it very simple. Let's say we could have this, okay? So there is refrigerant 134A in blue, and there is water going in green, no? Okay? So TB minus TA okay, so what's happening over here is that it looks like the water, so TB minus TA is 20 degrees. So that means that the water is actually gaining heat, no? All right? So then for the water to gain heat, what needs to happen to the refrigerant? I think this is something strange on the prime because the function of the refrigerant generally is to remove heat, no? Okay. But look in this case that this refrigerant is used to add heat. So what's going to happen? The amount of heat gained by one is the amount of the heat that is being lost by the other compound, by the other component. So here we can look at it in either way. Do we want to find Q from the water, the green, or do we want to find Q from the blue, which is the refrigerant? So we want to do, okay, so if we use the refrigerant, then we can say, so using so if we use the refrigerant, then what will be our system? Our system will be the refrigerant, no? Okay? So I don't know if it's coming in or out, but let's say the refrigerant, I'm going to assume that receive heat, no? Okay? Because it is what we need to calculate. So now, if I write down the first principle of thermodynamics or energy balance for the refrigerant, what would that be? It would be Q plus work. Then we see what is 0, no 0. Plus what? What do we have then? What is coming in? Refrigerant H1, no? And what is coming out? Refrigerant H2. Okay? So now we can go back to the question. Is there any work done on the refrigerant? No. But we know that either the refrigerant is going to gain or lose heat, no? Yeah? If it's positive, it will be heat going in. If it's negative, it will be heat coming out. Yes, what's the question?
I was going to ask, if we're considering heat here, how come we didn't in the first, we crossed it out? Or is that because of the amount gained is the amount lost by the other one, so the net will be 0? Is Q in the
If you want, you can look at it that way, but the other What you're saying is right, but the main reason why is because on the first problem, what is our system?
Everything.
It's everything. And what do you say over here? Neglecting and ignoring heat transfer from the outside to the condenser.
Okay, I couldn't read that. Great.
Does that answer the question? No.
Mm-hmm.
But what you say also is true because the Q will be 0.
Right.
And because this time, if you look at the overall, whatever this one is gaining is what this one is losing, so it's 0.
Yeah.
Okay?
Thanks.
But now when we just look at the water, then, or at the refrigerant, it's not 0 anymore, no?
Right.
Okay? So the whole thing is about the type of system you selected. Okay? So now, for this problem, what do you have? Q will be equal to what? Mr H2 minus H1. So you know MR, you can find H2 and H1 from the tables. So if Q is positive, if the value you get is positive, what does that mean? Is heat going in, no? If you get something negative, what does that mean? Is heat coming out. So we basically will be heat given by the refrigerant. Okay? So in this case, it looks like this should be negative, but I don't know, okay? You need to put the values. Okay, so now I think we are done with this problem. Is that correct? Okay, this is a typical problem. Okay, for this chapter. So this could be, I mean, doesn't mean you're gonna have it, but this is a typical exam problem as well. You need to go through everything, no? Okay, so you have more questions about the homework? Yes?
The same thing for 43.
43, yeah, I mean, let me see what 43 is. So maybe let me go to the next page. So page 90. Yeah, unless I have to put values, I try not to put values, okay?
Yeah.
So page 90, 443. So again, I need to see what that is. So 43 is this one, no? That's too much. Alright, see if I'm able to move this a little bit. Yeah. Okay. So let's see, 443. So air expands through a turbine. Doesn't matter if you don't know how to do the turbine, you can just do a rectangle. So, but what is the part of the engine of the turbine? Is the one which is going to expand. So generally that's the symbol for a turbine. But if you know how to do a turbine, just do a rectangle, okay? It's fine. So this is turbine. So air expands through a turbine. So there is air going through a turbine from, so 1 P1 equals 8 bar, T1 equals to 960 Kelvin, 2 1 bar, and 450 Kelvin. So basically, what is state 1? Is whatever is the state of the air on the combustion chamber, no? The pressure increased what? 8 times, no? From the atmospheric. And the temperature went probably from, whatever, 32 degrees Celsius, okay, to 98 to 960. So all this over here is what? Is really the enthalpy, no? Yeah? High enthalpy. I'm going to try to transform all that probably, I don't know what, but we'll see. So let's see. The inlets, okay, so that's good. The inlet velocity is more compared to the exit velocity of 90. So V2 is 90 meters per second. So how much is that in miles per hour? Can somebody do it quick? That's probably a lot. That's probably a lot, okay? What is it? Can you calculate it? So you know that it's big. So let's say V1, very small compared to V2. 201 miles per hour, okay? And basically, what should be the velocity at 1 if it was the ideal case? 0, because it's right after the compressor, no? So you transform all the kinetic energy into the compressor. So let's say much smaller probably will mean it's basically equal to 0. So the turbine operates at steady state. Which means the energy generated is 0. And what is always the goal of the turbine? Is to create work or power. And they say generate power of what? 250 kilowatts. So in an engine, that power is used to do what? To run the compressor, to turn the blades of the compressor, no? Yeah? Okay. Okay, so heat transfer between the turbine and its surrounding, and potential energy effects are negligible. So in this case, what I'm trying to say is that our system will be what? For this system over here, what is Q? 0, no? Okay? And this time, they're telling us to neglect what? The potential energy. But does that mean that the kinetic energy is 0? No. Okay? So modeling air as an ideal gas, so let's say air ideal gas, calculate the mass flow rate of air. So we need to find the mass flow rate of air. It's the only substance, so the mass flow of air. So let me just say this M, okay, of air in kilograms per second, and the exit area of, the cross-sectional area of the exit. In meters squared. Okay, so this problem I think is kind of similar to the first one, no? So what is the first thing we're going to do? So applying energy balance or first principle of thermodynamics, but I'm not going to write it down, to the system. What do we get? Is Q, so heat transfer plus power All right, I'll wait for you a second. So what is coming in? What is coming in? Mass flow of the air. Yeah, okay. But times what? So here I have to be careful. H1, but what else? Plus V1 squared over 2. All right? And now what is coming out? You're right, there is work, but it's already there. But what do we have? We have M H2 plus V2 squared over 2. Okay, so that's the general equation. Now, do we have any heat? No. Okay? Now, you need to be careful here with the values. What will be here the work? Is it coming in or coming out? It's coming out of the system, no? It's work done by the system. So really the value of this one should be what? Negative value, no? Yeah? Okay? So I'm going to keep it symbolic. So now, in here we need to solve for what? We need to solve for M. So this will give us what? So let's do some algebra here. So this will give us so power plus, let's say, M factor of H1 minus H2 plus V1 squared over 2 minus V2 squared over 2 all this will be equal to 0. So now, what do we know about this? They say V1 is very small. So what does that mean? We can probably neglect this value, no? For the difference. So now this will give us what? M should be equal to what? To the value for the negative of the power. So that will become positive divided by H1 minus H2 plus minus V2 over 2 squared. Okay, so in this equation, we know W, we know V2. Do you know H1 and H2? You can go to the tables, no? Okay? So you solve the problem. Now, okay, to solve for the area, I mean, how do you do? What is the definition? Is M equal to A2 V2 divided by V sub 2, no? By definition of the mass flow rate. So over here, you solve that A2 will be equal to what? M times V2, specific volume, divided by the velocity. From where do you get V2? The tables, no? Or maybe not. If you don't find it from the tables, from where can you get it? I think probably there's no tables for this one. My guess is that you needed to get it from the relation PV equal RT. Yeah? So that V here will be equal to RT. So I guess it's R bar T divided by P. Okay? And this one, this V2 is the one that goes over here. I think that's what happened last time in the problem we did. We said we could find it from the tables, but we needed to use the ideal gas relation. So do you understand the process? Yes?
Why was V1 equal to 0?
It's not equal to 0. They say that it's very small compared to V2. So once you do the difference, probably you have, let's say, 200 squared minus 5 squared. Is it going to make a big difference?
Okay. And then also, how did you determine it was ideal gas at 1?
It's because they say on the problem, consider air as an ideal gas. Anyway, air is always ideal because I only know air under the substance of gas. Okay? So more questions about the homework? Okay, so if not, let me look at the homework problems and let me ask you questions then. Let's see. So can you tell me all the homework problems so I can look at them? I mean, these ones should not be a problem. 51 was the homework problem?
Yes.
Okay, that should not be an issue. 50 was probably a homework problem, I'm guessing?
Yeah.
Okay. I mean, those ones I don't see any main issue, okay? What we did today, they're kind of similar. So this one is the same.
73.
73, we just did it.
Yeah, well, I was just reading off. 86.
Okay, let me look at 86. So 3 Rotan steam lines in a chemical processing plant enters the collection tank, operating at steady state at 1 bar. Steam enter in the water flow rate and quality 2.9. Now this one is basically the same that we did now.
97. Yeah, 97.
Okay, what I want to look is the ones that if you have this, some type of valve or. So 96 is part of the homework?
No. 97.
Okay, so this is the one I will say maybe let's look at it, okay? 97. So that one has no valves or anything. No, you don't have a single problem with some type of valve or throttling device. So this one, again, I mean, let's look at this problem over here, okay? I don't know what they're asking, but basically, in this problem, again, I have no idea what they're asking you, okay? But just by looking at it, the typical problem will be what? Is that this problem is probably long because you need first to consider the first system to be the compressor, no? I don't know what what do you need to solve for? Determine the mass flow rate of refrigerant and of the power. So my guess would be that you don't know, in order to find the mass flow rate, you might have to do the mass flow rate here of this refrigerant by doing this as the system, no? Okay? This one over here. So you can solve for the refrigerant. And then what do you need to solve for? The horsepower created by the compressor power. Okay, so probably I don't know exactly what to do, but what I would guess is that whatever you need to do generally this problem is that you first need to consider this as one system. I thought maybe then you need to consider this as another system. Okay? And then I thought maybe in this problem they were going to ask you the same thing as before, like what will be the amount of heat that is removed in the condenser, no? So the amount of heat removed in the condenser would be equal to what? To either the amount of heat that is gained by the air or the amount of heat that is lost by the whatever that substance is. It's also air, I don't know, okay, by the other one. Okay, so what you need to be careful is that you might have to use the same equation, but make sure that if you solve that in an exam, you clearly tell me for what system you are writing the equation. Okay, so 97, something else? Yeah, 100 is more the same, it's just longer. You don't have 98, no?
Yes, 98.
You have 98?
Yes.
Okay, so all right, so since I don't want to read everything and give you false hints, let me just look at the solution very quick. It would be easier for me than to read everything and try to guess. But every time they have a valve or a throttling device, jelly means that it's isotropic. Okay, so the fact that this is a throttling device, this is one assumption, but is true, is because the system is isotropic. You need to say that H3 will be equal to H4. Okay? Probably if you go to the class notes, we don't have it on the class notes, but so add it if you want to the class notes. So write down for problem what? 498. Problem 498. Throttling device means that the enthalpy at point 3 is going to be the same as the enthalpy at point 4. Okay? I think that's the only thing you need to know about this problem. Yes?
So whenever you have a valve like that, you can assume it's
Yes, in most cases it's a throttling device. So generally the assumption is that, the one is true, is that but we haven't covered that yet, is that is isotropic. So is S3 will be equal to S4. So basically what you mean is that on the throttling device, you are not gaining or losing energy, you're just transforming the energy to go faster, no? And the same thing will happen for a valve. Okay? So basically that means so valve or throttling device is always isotropic, will mean the enthalpy is equal on both sides. So I don't know what else to tell you.
What devices did you say that was? Throttle device?
Throttling device, yeah. Any if you have a throttling device or a valve, basically, if you have a valve, what happens if you have some water and you just close a little bit? You are increasing the flow, no? But you are not changing. If you look at the whole valve, any type of the amount of energy you are transferring, correct? Okay. Yeah, I mean, the other problems can be a little bit long and tedious, but if you apply the first principle of thermodynamics, making sure you use the appropriate system, these problems are not difficult, okay? And then go to the tables. Today we haven't practiced to go to the tables, but by now, hope tables, you are feel confident with the tables. All right? So guys, so the good thing and the bad thing about all this stuff is that you have spring break next week, no? So the good thing is that since you are giving a homework today, maybe I can give you a break for you to have a good spring break without any homework. So now the bad thing is that when you get back, we have classes, and then the following week you have the second exam. So probably what's going to happen is that week we cover some little bit extra material. I mean, I'll do whatever you want me to do, okay? Or I can do, and then I'll give you the choice. No, I know what I'm going to do. Okay, if you remember last class, we found the efficiency that, oops. We found the efficiency was equal to 1 minus Tc over Th, correct? But in the process of doing that, we went through this type of process, which is to find relations of volume, temperature, and pressure with that gamma over there, no? Going there. So what I'm going to do is that today I'm probably going to submit some problems, so a couple, 2 or 3 problems, I hope, about the next homework that will be what, homework 3 or 4? Homework 4. But that homework will not be due until not after the break, but the following week. So I think will be the 27th. Okay? So for the people that want to start working on this, they can start working on this. For the people that just want to go for spring break and have spring break, you can go and have spring break. No? Okay? But at least the choice is yours. And then on the way back, what's going to happen that week is that I'm going to start talking a little bit about entropy. Okay? Tuesday and Thursday, and I will add some problems for Tuesday. Okay? But this time it will not be like, and then Tuesday what I'm going to do is that I'll record a class, 27th, we'll record a class with whatever, 2-3 problems that I will pick up from the homework and I will do the solutions. Alright? I'll create a video so you can watch it. So you have the homework on the 27th, and then you will have the exam on March 29th. Yes?
So for the most part, aside from what's going to happen after spring break, what we've covered so far should be just on exam 2.
Oh, yes. Yes, probably on the exam 2, because I don't want you to, I want you to do good. So probably what I'm going to do is that it will be 3 problems. One, obviously, from this chapter, something like this. Another problem would be like, remember, like for the previous chapter, so this is for what type of system? Open system. I'll probably add the problem about what is the other type of system? Closed system. And I'll give you another tiny problem about entropy, or maybe about just know how to use those relations. We'll see how far we get into the entropy stuff. Or I might just leave the full entropy for the last exam, as I figured out, okay? Yes?
Since you are giving us a little bit of liberty, could the homework be due in a couple days? Like an extension? Instead of tonight?
No. No, because a couple of days, that means spring break. No?
I'm saying because there wasn't any homework on it.
No, I know what you're saying, but I mean, again, I don't look at the homework, so I think the greatest, if you submit it late, they are not being that picky. Okay? But again, I think I mentioned to you, this homework was going to be long. Last time when I came to class and nobody had questions, I was like, okay, I know what's going to happen today, no? All right, so have a good break, and see you.